Let's talk about friction. All right, we haven't had a chance to do this in class, so here we go. We're going to start off with a good old PHET simulation. Play around with friction a little bit. Here's our little guy. He's going to apply a force to this box. Can use this slider over here to change the amount of force. And notice if I push a little bit, there's an applied force and there's a friction force. And it shows you in those little arrows right there. Interesting to note, the friction force is actually changing depending on how much applied force I'm pushing. Also note that right now, the sum of the forces says 0. So I can click this up a little bit. We've got 150 newtons of applied force, 150 newtons of friction force, and the sum of the forces is 0. Also notice that we're not accelerating right now, so we have equilibrium. And I can keep moving this up, so now I'm up to 160, 170, 180. Interestingly enough, friction is adjusting to exactly match how much I'm pushing. Also, if we flip over to the other side, friction does the same thing. It's adjusting to how much I'm pushing. At a certain point though, 160, 170, 180, 190, 200, 220, 230, 240, oh, boop. Now look what happened. Now all of a sudden, my applied force is more than the friction force, and the friction force jumped down. Also notice that we're starting to accelerate, and we have a net force. Oop, and now friction's pushing the other way, slowing it down to a stop. Right? So let's do that again. Clicking it up, 250. Oh, that was too much. Let's go back down. Okay, good. So it looks like around 200. Now notice once again the applied force versus the friction. It's exactly matching it, and then as soon as I get up to about 250 or so, the friction force jumps down. Now, even when I change the applied force, the friction force stays the same. So there's something that happens with friction when you start moving. It changes a little bit, and it drops down, and it no longer can adjust. So this is all acceleration, right? And now we're slowing down, slowing down, slowing down, slowing down. Notice there's no applied force here, and we're just slowing down to a stop. There we go. Once again, now notice when the box is not moving and I'm not pushing on it, there's no friction at all. So let's take a look at this other page over here where I have some definitions of friction and different types of friction. First of all, my quick definition for friction is a force acting between two surfaces that are touching. Easy. Also, note that friction always acts parallel to the surfaces. It always opposes the motion. And the source of friction is actually microscopic irregularities on surfaces. I just grabbed this image from the internet, and you can see that what might look like a smooth surface microscopically is actually full of a bunch of bumps. And these bumps have to move over each other. That's what's going to create friction. Now we can move down here. There's actually two flavors or two types of friction that we can talk about. First, there's static friction, which is between two objects that are stationary. Static means stationary, just like we had static equilibrium. Something interesting about static friction is its magnitude can change depending upon the situation. So it can start anywhere from 0, and then it gets up to a maximum amount depending on the situation. So I like to call static friction smart because it can adjust its magnitude depending on the situation. It can go anywhere from 0 and go up. Let's go back to the simulation. So here's static friction, and I'm pushing, and static friction is adjusting. However much I'm pushing, it's matching it. It can switch this way, it can switch that way, right? Up to a certain point. Once you push past the maximum static friction force, then you jump into the realm of kinetic friction. And once again, kinetic friction, as you'll see on my next thing, is not smart, right? So here we go. Let's talk about, first let's say the maximum static friction is called peak static friction. And then if a bigger force is applied, then peak static friction, then object will move. Then we move over to kinetic friction. Kinetic means moving. So this is between two objects that are sliding relative to each other. The magnitude is constant, or nearly so, and so that means that kinetic friction is not smart, meaning it's not going to adjust your level depending on how fast you're going. It doesn't depend on how fast you're going. It doesn't depend on how hard you're pushing. It's just one number. Generally, it's going to be smaller than static friction, and that's what we saw as well. So there's no way to actually predict for sure how much static friction or how much kinetic friction you're going to get, except for just starting to apply forces to things. So for this situation, looks like about 250 or so, and I jump down into kinetic friction. Now, as soon as I move, that kinetic friction is staying at 184, right? Switching over to this side, I'm moving, okay, moving, 184. It's always 184, right? Unless I stop, reset, go back to static friction, and now it can adjust. So the lab that you're going to do is you're going to be checking out surfaces and moving things around, and you'll be seeing which, measuring the static friction force, the peak static friction force. So this is the point where it just barely starts to move, and then you'll measure what that kinetic friction force is. And you'll see that in the lab instructions. Have fun.